counting in Calabi-Yau categories. So Fabian, please.
Yes, thanks again, Jan. So last week I started, basically didn't talk about my own work. It was more background and motivation, sort of problem statement. So I covered roughly the first 3 points. I talked about what this homotopy cardinality is, how it's used to define whole algebras, and how it's related to not polynomials. And then I mentioned some situations where it's sort of not defined, but you expect there to exist a definition. So maybe that's maybe the one point I'm going to review today. Sort of what was the problem statement in a sense? What are the problems that we're trying to solve? And so one example was in this whole algebra business. Yeah, let's look at this elliptic whole algebra. So you take an elliptic curve over a finite field, take its category of coherent sheaves, and that has a whole algebra in single whole algebra just because it's an abelian category and finite enough. But the whole algebra looks like half of what it actually wants to be. It's like half of a much nicer object, which is its Drinfeld double, which is called the elliptic whole algebra. And you kind of expect that you should get this elliptic whole algebra, this Drinfeld double, directly somehow from the Z mod 2, the category of Z mod 2 graded complexes of coherent sheaves on E. But there's sort of no intrinsic construction here. So that's going to be a special case of what we're going to define. And another example is in knot theory. So the knot theory part was a bit quick last time, but yeah, the main point is the following. So there was a result here of Ng-Rutherford-Shende-Sivek, which tells you that if you have a Legendrian link and it's degraded, means that roughly that the winding number along the knot has to be 0, the total turn, then you can assign to it 2 things. On the one hand, it has this ruling polynomial P sub L, and you specialize that to square root of Q minus 1 over square root of Q, where Q is some prime power. And then that is the same thing as essentially the homotopy cardinality of a DG category that you assign to the Legendrian link. So the C1 LFQ here, this is some DG category over FQ. It's called the augmentation category. You can think of it in Fukaya category terms as somehow surfaces, Lagrangian surfaces ending on this Legendrian knot. And sort of counting those in the correct homotopic sense using this homotopy cardinality gives you this ruling polynomial. And if the link is only periodically graded, so Z mod M graded, for example, Z mod 2 graded just means oriented link. So every Legendrian link has some orientation. So everything is Z mod 2 graded. The right-hand side is always defined. That's not a problem. But the left-hand side, then the DG category becomes a periodically graded category, and homotopy cardinality sort of doesn't make sense a priori. But since you have a candidate for what it should be, maybe there is secretly some kind of definition that works. So that's going to be another application. We're going to generalize this to the case when everything is periodically graded. And so first of all, the problem is defining the left-hand side and then showing that the 2 are the same. Okay, so yeah, now coming to kind of the stuff that is actually the new stuff in our paper. And I want to start with the main idea, which is actually quite simple. So suppose we have a DG category over a finite field, and also should be very finite in the sense that it's finitely many isomorphism classes of objects. And then the X, so that the HOMs from X to Y shifted by I should be all finite dimensional and should vanish for big enough I, so only finitely many non-vanishing. Then we can define these kind of alternating sums of dimension. So the Euler pairing would be taking the alternating sum over all integers. I also want to consider now doing this for some subset of the integers, in particular the negative integers. And then you have the following formula for the homotopy cardinality. So the homotopy, so when C is a DG category, the C tilde was essentially like its space of objects. So concretely, it was take this DG category, take its DG nerve. That's a quasi-category or infinity one category, and then take the maximal Kahn complex. So remove everything that's not invertible. You get some Kahn complex, which is some way of talking about spaces. And it has a homotopy cardinality, and we can, instead of doing all that complicated stuff, we can write it very simply. It's the sum over the isomorphism classes of 1 divided by the size of the automorphism group. And then there's some power of Q, which comes from this alternating product of higher homotopy groups, sizes of higher homotopy groups. And so since everything is now linear, we can write that as Q to the power minus the alternating sum of the X groups, dimension of X groups, over negative I's. That's what this definition means.
I have a quick question.
Just rewriting.
I have a quick question for the CPU DT category. The isomorphism classes. Now, isomorphism means in what sense? Quasi-isomorphic or with isomorphic?
Isomorphic in up to kind of homotopy, yeah. So
okay, so that's the with.
Yeah, whenever I say isomorphism in a DG category, I mean it has some map which has inverse up to homotopy. Yes.
Okay.
Thanks for the question. Yeah. All right. So just rewriting this kind of big alternating product in terms of the power of Q, and we can clear, right? So if the category is only periodic, so if the dimension of these X to I will be then periodic in I, then this is going to be ill-defined because it doesn't. This second condition here will be no longer satisfied. But now, if we turns out if we impose a little bit of symmetry, then we can relax the finiteness condition. So the symmetry that we'll impose is that the category is Calabi-Yau. So Calabi-Yau, these are the simplest. There's different versions, but the simplest one is to say that you have a kind of Poincare or Serre duality in your category where xi between two objects is isomorphic to the dual of xn minus I, or an n-dimensional Calabi-Yau category. And then the objects go the other way. So xi from x to y should be dual to xn minus I from y to x. So examples are category of coherent sheaves on some Calabi-Yau variety, in particular elliptic curve, which is this example that I mentioned as motivation. Yeah, but now we want to assume not that it's odd, but that it's even dimensional Calabi-Yau. And then you can rewrite this sum over negative X groups, right? So the Calabi-Yau means roughly that all these negative X groups are going to be dual to the positive X groups up to some shift. So that means that the sum of dimensions over the negative X groups, alternating sum, you can rewrite as, the sum over all degrees, which is this Euler pairing, minus the alternating sum only of the degrees between 0 and n, and then divide by some factor of 2. This is possible for even n. And this looks kind of promising because, it's not quite. So this term here looks good because this is defined now for more general categories, which are not necessarily only infinitely many degrees. You have x's. But the first term is still somehow an issue. But the second term is actually kind of a little bit more maybe sensitive, right? So that the first term is Euler pairing. This term here only depends on the class of X in the Grothendieck group, whereas this really depends in general on the isomorphism class of X. So somehow the second term is here the more important or interesting one.
So, Kate, can you explain why you ruled out odd dimensional? Because people, for example, n equals 3, people are interested in 3-dimensional Calabi-Yau, which is not in your class.
Yeah, so if n is odd, then I don't get this formula. I cannot rewrite. We're going to see what this formula kind of buys us, but Yeah, if you try to rewrite, if you try to do the same, if you try to rewrite this thing for odd n, then you don't have a formula like that.
I understand that you cannot just use the same formula, but many people like to count objects in whatever, something in odd
I mean, for sure.
probably.
Yeah, we would like to have odd as well. We just don't know how to do it, I guess is the answer.
Okay.
But I mean, it will turn out that because you can do this for even n, you can define the Hall algebra for odd Calabi-Yau. So there's a kind of shift going on. So Hall algebras will be defined for odd Calabi-Yau categories. I'll explain where that comes from, that shift. But yeah. But for now, this argument here uses even n. For example, it could be a category of local systems on some even dimensional closed orient manifold, or even dimensional Calabi-Yau.
Your odd appears as boundary of something even.
That's right, essentially, in some sense.
Okay.
So the second term is fine if we have a little bit less finiteness. So if we, instead of assume that these xi vanish for almost all I, we'll assume only that they're all finite dimensional, and this we call degree-wise finite. That's not completely standard terminology. But degree-wise finite means you have possibly xi in infinitely many degrees, but in each single degree, it's finite dimensional. And so then definitely this term here will be well-defined in this more general setting. But the first term is not yet defined. However, turns out we can just sort of forget about that term or renormalize it away. It's related to this twisting, which I talked about for Hall algebras, since it's the Euler pairing in some sense. So the effect of removing this term will be, roughly speaking, that from the very beginning, we get the twisted Hall algebra instead of the untwisted single Hall algebra. So it actually has some nice effect of automatically giving us this sort of nicer twisted version of the Hall algebra, which is then related to quantum groups and so on. This now motivates the following definition. So if we have a DG category, finitely many isomorphism classes of objects, we now assume only that it's degree-wise finite. So in particular, it could be a periodically graded category. And we assume it's Calabi-Yau, some even dimension. And then we just define its homotopy cardinality. I mean, basically using that formula as a replacement, right? So in the previous formula, there was this term, and then we just replaced that term by this guy, but omitting the x, x Euler pairing, and we get this formula here. Okay, so it's just some definition at this point, and it's not really clear how useful it is. Also, this condition here is pretty restrictive because like DG categories usually have an infinite number of objects, isomorphism classes of objects. So this by itself is not yet super useful. However, a relative version of all that will be much more useful. So relative means that we have now not a category that's Calabi-Yau, but a functor that's Calabi-Yau. And this sort of notion was invented by Toen and Graf Dickerhoff. And I'm going to need, there's kind of different variants again of this definition. What I'm going to say is known as weak because it's not cyclically invariant, possibly, and it's right. Calabi-Yau, right means that my categories are they're kind of degree-wise finite. You could also have left, where your categories would need to be smooth. And if you remove the weak, you need some kind of cyclic invariance property. So in this version, the one that I want to use, what is a Calabi-Yau functor? Well, first of all, the target needs to be a Calabi-Yau category of dimension 1 less. So think of this as like if you thought of a Calabi-Yau category as somehow being analogous to a oriented closed manifold, then this will be analogous to a manifold with oriented manifold with boundary. And so think of B as a kind of total, this manifold with boundary, and A is its boundary. So we have we want an n Calabi-Yau, n-1 Calabi-Yau structure on this target, the kind of boundary.
And B is also Calabi-Yau. I'm confused. Only one is Calabi-Yau.
Yeah, not only A is Calabi-Yau, and then the functor will be somehow Calabi-Yau.
Yeah.
Which, yeah, if you think about if you have maybe the order would be better to say this here. So if you have a manifold with boundary, then instead of point graduality, you have some long exact sequence in cohomology, which involves the cohomology of the manifold that has the boundary, and then the boundary of that manifold. And basically, you axiomatize that property for a functor. You want some long exact sequence like that, which is somehow reminiscent of this long exact sequence for a manifold with boundary. And then there's a bit homotopically better way of saying what is long exact sequence. More precise way is saying that you have a homotopy bi-Cartesian square, so a fiber sequence of bimodules where B goes to pullback. So this is the diagonal bimodule over B. This is the pullback of the diagonal bimodule for A. And we, by this using the functor and the Calabi-Yau structure, we can send it to the K-dual of the diagonal bimodule shifted. So you have these two maps, and then you have a homotopy bi-Cartesian square, means that this you need a homotopy between this composition, right down, and the zero map, which is this composition. And the whole thing should be homotopy bi-Cartesian, which means roughly that this long exact sequence should exist.
Is it equivalent to what Braun and Dickerhoff called Calabi-Yau category with boundary?
Because I'm not sure they call it that, but what they call like a relative Calabi-Yau structure. Yeah.
Yeah, because I'm asking because there is a further generalization which is not published, but which is due to it's part of our work with Maxim on Riemann-Hilbert Calabi-Yau with corners. So you do not have just a pair; you have the whole diagram of categories. Like imagine that you have a manifold with corners.
Yeah, I'll actually come back to that. So just hold that thought. But this is not this yet. This is really just manifold with boundary, not corners.
Yeah.
But the corner stuff can also be incorporated in the story. Yeah. So an example would be take the category of local systems on a compact-oriented manifold with boundary. And then this has a functor just restricting to the boundary to the category of local systems on the boundary. And the boundary is compact closed oriented. So this is a Calabi-Yau category of dimension, whatever the dimension of the boundary is. And then this functor here, for this functor, you have this long exact sequence. And so this gives you an example of a Calabi-Yau functor. Another example, this is more out. Maybe I should say this in a more geometric language. As Jan said, everybody knows about Fukaya categories. So what this example here secretly is you take the Fukaya category of a disk with n+1 marked points on the boundary. And then algebraically, that's the same as the derived category of an AN quiver. And so you have this disk with n+1 marked points on the boundary, you can restrict to the boundary. So that's just n+1 points. That's the category of this semi-simple algebra k to the n+1. So this is the target here is a 0 Calabi-Yau category. So this functor here is a 1 Calabi-Yau functor. And more generally, in symplectic topology, you get lots of these relative Calabi-Yau. If you have some Landau-Ginzburg model and it has a Fukaya-Seidel category, and you restrict as a functor to the Fukaya category of the fiber, and get lots of those kinds of relative Calabi-Yau functors. Okay, and in particular, this second example will be important later because it turns out that this is related to Hall algebras. Yeah, now what I did before this kind of trick where I rewrote the homotopy cardinality in some way that makes sense for more general categories, which are only degree-wise finite, and you can do the same trick for in this relative case. So assume that you have a DG functor over some finite field, DG categories over FQ. We need the induced map on isomorphism classes to have finite fibers. We need A and B to be, assume first that we're only locally. So we will eventually generalize to the case where A and B are only degree-wise finite. But for now, assume that they are locally proper, so that there's only finitely many degrees where their x are non-zero. And assume that this f is a Calabi-Yau functor for some even dimension. So it's like an even dimensional manifold with boundary. And then there's a kind of generalization of, so in the absolute case, I wrote this here without the f terms, and this term here, I had an n instead. So this is the generalization of that previous formula. So using this long exact sequence of the Calabi-Yau structure, the relative one, you get this identity. And what does it tell you? So you see that there's a factor 2 here in front of this alternating sum over dimensions of x groups. And here there's no factor. And then this means this is exactly the term that appears when you try to pull back half densities on the space of objects on B, the target, the source, to this kind of, I meant your half densities on A to measures on B. Yeah, so I got A and B got switched around. So you have half densities on the target and measures on A, where the half. So what does that mean? So if you try to, for example, pull back measures to measures, then you would not have this factor 2 here, and you could not rewrite all of this in such a way that makes sense more generally. So only if you do only this particular combination here, or any multiple of it, will work. So you can rewrite it again. Everything here makes sense in degree-wise finite setting, and we drop this first term again, some kind of twisting that we ignore, and then we get some definition of. So we now have a DG functor of FQ. What has changed is instead of that, we are only degree-wise finite now. So our X groups could now be non-zero in infinitely many degrees. In particular, A and B could be periodically graded categories. Still, I want finite fibers for the induced map on isomorphism classes, and I want this function to be Calabi-Yau for some even n.
What is a basic example for this infinite? I mean, I understand that you will need periodic for the purposes you mentioned previously, two periodic, whatever. But what's a real-life example of this?
You mean of something that's degree-wise finite but not periodic, or just the full setup?
Yeah, well, maybe even periodic, but something which appears, which has infinitely many X groups, but still.
So yeah, the main examples I know are kind of periodic categories, right? But so there's also, when you do kind of define some cluster categories, which are defined by localization. And if you're not in the thinking case, then these are not generally going to be periodic, but only degree-wise finite.
Okay.
So, there's some examples coming from kind of cluster theory. But mainly it just, in the beginning, when we wrote this paper, we wrote periodic everywhere. And Misha realized that we don't actually need that. We can just put degree-wise finite everywhere instead. And there's no additional complications.
So then the example you mentioned, it's cluster categories with Calabi-Yau structure, something like that, yeah.
Yeah, so it's something like you have some quiver with potential, and then this has this Calabi-Yau 3 category of perfect modules, and you localize by subcategory of finite dimensional modules.
Yeah.
And this will be Calabi-Yau 2 category. And if the quiver is not ADE.
Yeah, but sort of analog of a non-compact, I would say, manifold after localization.
Yeah, maybe, but it's still kind of degree-wise finite, turns out.
Yeah. Okay.
But yeah, it's not periodic. Yeah, I don't really know examples like very well where my main motivation were periodically graded categories, but yeah, doesn't really change much in all this formalism. Right. So when you have one of those functors, we now define what is sort of if you have a half density on A and you pull it back to a measure on B and then integrate that in some sense. So that's a map from complex linear combinations of isomorphism classes of objects in A to the complex number. So let's kind of think of this as integrating these elements. And okay, it has some explicit formula, and that formula comes from this this previous thing here. So that would be in that locally proper setting, I would have some formula involving this term, and now I just replace it by this other term, which I get because my functor was even Calabi-Yau, and replace it by that. So it looks kind of ugly, but yeah, there's like a conceptual explanation for where the formula comes from. And the justification also for this is a kind of functoriality. So yeah, maybe before I talk about that, I talk about some analogy here with supergeometry. So if we have a DG category, yeah, somehow I want to think of it as analogous to a superspace, because right, what's a tangent space to the space of objects in the DG category is like a Z-graded, maybe Z-graded space would be more correct. So it's not superspace is like Z mod 2 graded, but yeah, really Z-graded. And then an odd Calabi-Yau structure is well, gives rise on the space of objects to an odd symplectic form. So these are analogous, or more precise statement actually, that if you have the thing on the left, then you get the thing on the right, sort of on the space of objects of your category. If you have a Calabi-Yau functor, then that induces a Lagrangian kind of map or subspace on the space of objects. So the Calabi-Yau functors are analogous to Lagrangian subspaces in symplectic and odd symplectic spaces. I want to think of these. I mean, there's some crude kind of version, but I want to think of as finitely supported complex valued functions on the space of isomorphism classes as analogous to half densities, or that's the role that they will play in this formula. And then somehow what's true in supergeometry, so when you have an even symplectic form, you have this Liouville theorem, you have a natural volume form. But when you have an odd symplectic form, what happens is that you can instead, if you have a half density on your space, then you can integrate that invariantly over a Lagrangian subspace. So this integral here doesn't depend on any additional volume form or anything. Just the fact that L is Lagrangian and that alpha is a half density, and that you have an odd symplectic structure. And so the analog of this is this kind of functional that we define. That was on the previous. So this here, what has a slightly complicated formula, I want to think of as analogous to integrating a half density over Lagrangian subspace. Yeah, and these structures on the right appear in this Batal-Minkowski formalism for quantum field theory. and kind of where, as I understand, kind of for some Lagrangian subspace, I mean, in quantum field theory, all of these things are also infinite dimensional, but what happens somehow that you pick one Lagrangian subspace and the integral doesn't make sense, and then so you deform that Lagrangian subspace by some isotopy, and then now suddenly the integral does make sense, and by invariance under isotopy, the two integrals should be the same, even though one is sort of ill-defined and the other is well-defined. Yeah, I should say I would like to make this sort of a bit more precise, this correspondence, but I don't fully understand. Like, what is there some common generalization or something? Okay, so this just serves as maybe some geometric intuition for what's going on. Yeah, now I want to talk about some other justification for this formula, which is a punctuality property. So yeah, instead of manifold with boundary, you can sort of think about Bordisms, manifold with some ingoing and outgoing boundary, so that the category analog of that is you have a DG category, and the span of DG categories, so that the combined functor to the product B to A1 cross A2 is a Calabi-Yau functor. So these things are called Calabi-Yau spans. And
so
the main
yeah, maybe since it's time for analogies, yeah, yeah. I mean, if I'm not sure that it's the right analogy, but anyway, if I try to make, there was this old idea of Alan Weinstein about the category of symplectic manifolds, yeah.
That's right, yeah. So there's somehow two ways to think about these spans geometrically, either a manifold with either a Bordism or as a Lagrangian correspondence.
Yeah, that's what I mean, yeah, okay. Good.
So you're right, this is some kind of non-commutative analog of the morphisms in this Weinstein symplectic category.
Yeah.
Yeah, thanks for pointing that out, yeah. So the main thing about these Calabi-Yau spans is that they can be composed, right? Which, if you think of them as Bordisms or as Lagrangian correspondences, then that you could guess that something like that should be true. So what it means precisely is that if I have two of these Calabi-Yau spans, I can compose them by forming this homotopy pullback square. So it makes sense to talk about what's our Cartesian, what's a pullback square of DG categories in the homotopical sense. And then it turns out that the composed span is again Calabi-Yau. Yeah, basic result. And now that means we can form a kind of category where the morphisms, so this is some non-commutative analog of this Weinstein symplectic category, the objects will be, before we do that, yeah. Well, if we have one of these Calabi-Yau spans, we get a linear map from it by, yeah, basically, so I said there's a natural inner product on the space of functions, finitely supported functions on isomorphism classes of objects. This has the obvious inner product, and because they're, I think of them as half densities, there's no factor, there's no weighting when I form the inner product. So it's just a completely standard inner product that doesn't take into account the homotopy groups or the X groups. So this is an inner product space, and therefore, instead of saying I have a functional on the space of functions on A1 cross A2, I can sort of, using duality, I can trade in and get instead a linear map from the set of functions on isomorphism classes of objects on A1 to the set of functions on isomorphism classes for the category A2. And the formula, yeah, basically determined by what I said. So take the previous formula and then apply duality in one of the factors. So now we're kind of linearizing now spans, right? So given one of those Calabi-Yau spans, we're turning it into a linear map between vector spaces. So maybe it's like a pre-quantization functor, if you want to use fancy language. And well, I said functor, that needs some justification. So yeah, so first of all, form this category where so we fix some finite field, and now we look at the category where objects are these degree-wise finite n-1 Calabi-Yau categories, so odd-dimensional Calabi-Yau categories, and the morphisms are even-dimensional Calabi-Yau spans between them, up to some equivalence, some finiteness condition on the left leg of the span, and then the composition in this category is composition of Calabi-Yau spans. And then a theorem that we prove is that this linearization is really a functor. So it means if you compose Calabi-Yau spans, right, then for the composed span, you need to show that the linear map you get is the composition of two other linear maps. And yeah, there's some justification for calling this a theorem. So this is not, I mean, it's not super difficult to prove, but because our whole thing is defined by some explicit formula here, actually verifying functionality, it takes a bit of work. It's playing around with lots of long exact sequences. It's not completely trivial that this is a functor. But this you can view as some justification for this definition here, saying that it has some functionality properties. Okay, that's the sort of main result we prove about this L, and then we have some applications. But before I talk about applications, going back to what Jan mentioned, so instead of having a span of Calabi-Yau categories, you can have, or of anything, you can talk about two spans and higher spans. So as a two span, I want to understand a diagram of this form. And what it will correspond to geometrically is, instead of manifold with boundary, manifold with corners of increasingly high codimension. And these n spans form n morphisms in an n category of spans. Yeah, and now this is the point where it gets a bit more category theory heavy than actually I'm comfortable with. So we actually don't do this generalization only for two spans. So two categories I can still sort of think about, but higher categories I find a little bit challenging. But in any case, so there's a notion of Calabi-Yau structure on these higher spans, and this can be sort of contained in work of Shende-Takeda, and then more explicitly in this work of Klist, Digerhoff, and Balde on complexes of stable infinity categories.
Our definition with Maxim, I don't know how, I mean, when you explain the analogy, of course, it's the same, but like we do not need really very, very high categorical structures, and for that, I'm sure it's more explicit than those people wrote down, but there is a kind of equivalent definition even for the Calabi-Yau algebra, which uses non-degenerate cocycles in negative cyclic homology. That's our paper of whatever, 20 years old, I believe. And there is a similar story for this, which generalizes that old story to relative, to say cubic diagram of algebras and so on, so on, so on. So then I believe, I'm not sure that the non-degeneracy of some cocycle in some total complex is equivalent to the diagram, say, which you are mentioning, but maybe there is a kind of a more down-to-earth way to describe that you do have some whatever de-Calabi-Yau structure on a collection of categories. Kind of a basic example.
Yeah, and I think what you're saying is something to that effect is proven in this work of Christikov and Walder, that if you go to some kind of total complex, you have a... So I'm not saying that the definition of what is a d-Calabi-Yau n-span requires higher category theory. But sort of all the composition, now you have this analog of composing two spans will again be Calabi-Yau span, and to kind of formulate all that, that only makes sense in sort of higher categorical language. Yeah, but just to define what is a d-Calabi-Yau n-span does not require higher categories.
Okay, so that's good, because for us, kind of a basic example is the following. You have a complex symplectic manifold with some partial log compactification, and you take just categories of compactly supported perfect modules for each of these, and they form some cubic diagram, which is an example of this Calabi-Yau category with corners, or Calabi-Yau structure on this cubic diagram. And it's a very kind of intuitive. So because all the functors come from restrictions, so then, you know, otherwise it looks a little bit scary. So I didn't read this Shende-Takeda, because we wrote it kind of many years ago. So maybe it's equivalent, but maybe not. I don't know. Okay.
Yeah, it sounds more or less equivalent. Yeah, I mean, what you're describing is sort of the algebro-geometric analog of manifold with corners, if I understand.
Yes. Okay.
Yeah, there's also symplectic analog, which is having like a Landau-Ginzburg model with like several potentials.
Yes, that's another.
Your fiber is now a Landau-Ginzburg model itself, and then
Yeah. Okay. Good.
Yeah. Super. So these things are quite natural, and we don't really develop all this. Everything that we do for one spans should generalize to n spans, but we don't really do that in the paper. Except we do a little bit two spans because we need that for knot theory, it turns out. So a Legendrian tangle will give us a two span. Yeah, that's a remark. Okay, so let me say what are applications. So how do we solve these two problems that I mentioned originally about defining Hall algebra and about this knot polynomials? So take a degree-wise finite n Calabi-Yau category over a finite field of odd Calabi-Yau dimension. And then we have a Calabi-Yau, even Calabi-Yau span. So we remember that the span which was used in the definition of Hall algebras is the one where at the apex you have the category of morphisms in your category, or functors from A2 into your category. And that maps to C cross C on the one hand and maps to C on the other. So you can think of morphisms also as triangles, and then what you're mapping to is either Z and X, the first and third object, or the middle object, Y, the extension of the two. And the Hall algebra product was a kind of pull push along this span. And now under our assumptions on C, this span will be an even Calabi-Yau degree-wise finite category. So it will be one of those spans where we can apply this functor L. We can linearize the span. And the linearization will give us a map, a bilinear, some kind of product on the space of functions on isomorphism classes of C. And, well, we want that to be an algebra, so we want it to be associative. And associativity follows exactly from this functoriality under composition of spans. So there's a bit of a diagram here about the proof. So this is kind of how you prove universally that the Hall algebra is associative. So you have a triple of objects, and then you can either first compose the first two factors that's going down, and then compose them one way that's going down and right. Or if you have the other parentheses that's going right and then down, and then you can compose these two spans here. So this is a homotopy pullback square. This is also, so the composition of the two spans is the span which has apex, the set of pairs of composable morphisms going down to triples of objects. and the other leg goes down to a single copy of C, right? So that's the kind of composition span. It gives you composition of 3 objects in the Hall algebra. And because of all this diagram, it's commutative, and this is homotopy Cartesian. The functoriality implies that the whole algebra product is then associative, if defined in this way. Okay, so we get some, for any degree-wise finite odd Calabi-Yau category over a finite field, we get some whole algebra of it. So in particular, it will apply to periodically graded odd Calabi-Yau categories. So that was the first. Yeah, and also you could wonder like a more explicit definition or a formula for this whole algebra product, which looks a little bit complicated. So it's like not something that somebody would have invented without this context, I think. I mean, the basic formula, right, to take the product is the sum over extensions, but the question is what precisely should be this power of Q? And that's a slightly, I mean, some formula which involves the rank of some maps on X groups. It simplifies a bit if n is equal to 1, particularly if the thing is Z2 graded, then n
is a dimension of your...
n is the dimension, the Calabi-Yau dimension.
Yeah, okay. What about n equals 3? Does it coincide with our formula with Maxim, or it involves more X groups?
Well, you kind of assume that the thing is not periodic, right? But
no. Like you said that periodicity is not. I mean, periodicity is not essential. Yeah. You said that.
I mean, it will recover the usual Hall algebra when the thing is not periodic, when it's just locally proper.
Okay.
Yeah, but maybe the twisted version of that, right? Twisted Hall algebra. But yeah, the main point is that you can write down something even if you didn't have any other definition of Hall algebra before. For example, in this periodic setting.
Okay.
Yeah. And so you write this thing down and it looks, yeah, it's actually quite hard to prove directly that it's associative, but it follows from our general functoriality statement. Yeah, and somehow we show also in our paper that lots of constructions, sort of ad hoc constructions of Hall algebras, they all coincide with this thing whenever the two are defined. So there's lots of...
I'm a bit confused because you mentioned, at some point you mentioned this Bridgeland story with attempt to construct a double of the whole algebra. Yeah. No, but using just 2 periodic complexes. But if I have a whole algebra, probably I miss some important. If I have a whole algebra of an odd Calabi-Yau category, yeah, like the one which you define, can I construct it double?
No, it's just an algebra right now. But the point is, yeah, so if you took the abelian category and take the double, then that's going to give you the same thing as our construction. So I had this diagram of the elliptic Hall algebra and this missing dotted arrow. How do you get from the Z mod 2 complexes to the Drinfeld double? And then that dashed arrow is now filled in with this construction.
Yeah, but it's a kind of a specific example of n equal 1. Because your Calabi-Yau is one-dimensional, yeah, and you double it, something like that, which Bourban and Schiffman, I believe, did without this higher mathematics. But if I try to do it for n equals 3, because we have something which I really want, I mean, for 3-dimensional Calabi-Yau, some toric Calabi-Yaus, we do have whole algebras which I wish to double, but I don't know how to do that. So the way okay, maybe it's for the discussion part, but anyway, it's a question.
I mean, if you have any kind of abelian category, which is odd Calabi-Yau, you can take 2 periodic complexes in that.
Yeah.
Then you can apply our construction. And that would be some kind of double of the Ringel-Hall algebra.
Okay.
And this kind of two periodic complex that reflects the Drinfeld double construction. Is that correct? Because you are doing it in the categorical setting, but when you perform this whole algebra construction, is that because the Drinfeld double construction is purely algebraic? You have half algebra, you can always go with the double.
I'm not sure I acoustically understood your question. So are you asking?
So
can you repeat the question?
Drinfeld double is a purely algebraic construction. It's not
Yes.
the underlying algebra. You have some sort of a half algebra and a co-multiplication. With this pairing, you can always play with that. But when you say you have this Calabi-Yau category, if you go with the Bridge-Next construction, go with a double with two periodic complexes, and then using your construction, you get algebra. So my question is, this whole algebra is that the Drinfeld double of the original one or not?
Yeah, we show whenever it agrees with the Drinfeld double when as an algebra, whenever that doubling construction is. So whenever you have like odd Calabi-Yau abelian category, roughly speaking. So in Bridgen's construction, he doesn't need anything to be Calabi-Yau, but we do need Calabi-Yau.
Okay. So that's also back to Jan's question, but N=3, that's what we cares the most. So N=1 is because of many things algebraically, the whole algebra is very nice, and that the whole algebra structure, everything was quite clear that was done. But for the N not equals 1, and not in the hereditary, abelian category case, that's not in the non-hereditary case. So does that also work? That's my question.
I see. Yeah. So you're saying if the category is not hereditary, then you don't have a co-algebra structure.
That's the point. I was going to wait till the end.
There's still some ad hoc construction you can do, I think. Which is, it's like Bridgen's construction.
Okay.
But this will be a nicer kind of completely intrinsic from the category of two periodic complexes.
I see. So you don't have to have this.
We don't need to talk about exact categories and abelian categories. Yeah.
Okay, thank you.
Okay, so this is the explicit formula, and it's so examples of odd Calabi-Yau categories where we can apply this is two periodic complexes coherent sheaves on some elliptic curve, finite field, and it agrees with this Drinfeld double construction. Another potential example is you take the Fukaya category of a hyogenous surface. So that thing is not Z-graded if the genus is bigger than 1, but only periodically graded. And so we can now define a whole algebra of that Fukaya category. And I believe it will be related to some Legendrian skein algebra. But I don't know what the precise statement, but what you get, I expect to be somehow some kind of skein algebra.
I'm confused why it's odd-dimensional Calabi-Yau.
Why the category should be odd-dimensional? Or?
Yeah, why you take just whatever genus 5 surface, take the Fukaya category.
That's a Calabi-Yau 1 category, but in the Z mod 2 graded sense, yeah.
In Z2, okay.
So I guess when you're Z mod 2 graded category, also it only makes sense to talk about even and odd Calabi-Yau. The Calabi-Yau dimension is only defined up to the period, right?
Okay.
Another more generally, if you have a Fukaya category, the Fukaya category in general is defined over this Novikov field. So, but we need it to be defined over a finite field. But if your symplectic manifold is what's called monotone, so that the class of the symplectic form should be proportional to the first term class, then and it's odd-dimensional, then the Fukaya category is defined over integers. So you can base change to a finite field, and we can define the whole algebra of that. And yeah, I don't know what this whole algebra will be.
Yeah, but if you want over in characteristic 0, you work motivically probably.
Also, yeah. So that's yeah. Thanks for. So we don't need this monotone if we upgrade our entire construction to motives instead of just counting over finite fields. Yes, that's right. Yeah, and so mirror dual to these kind of things are some categories of matrix factorizations. So they also provide examples of some categories where we can now define a whole algebra. Then just see how much time. I'll just briefly mention this other application. So if we have a Legendrian link and assume it's only Z mod 2M graded now, not Z graded, we get this augmentation category over a finite field FQ, which is also graded by Z mod 2M. And yeah, it turns out that this augmentation category is not itself Calabi-Yau category, but it's very close to being a 2 Calabi-Yau category, right? So this augmentation category with some Lagrangian branes ending on this knot. So they're almost two-dimensional surfaces, but they have some boundary. So what is true is that you have a functor from the augmentation category to the category of rank 1 local systems on the underlying link L. So L here just regarded as a one-dimensional manifold. That's a 1 Calabi-Yau category, and this functor here is 2 Calabi-Yau. And that's in the Legendrian knot theory literature, that's known as Sobolev duality, essentially. And so, yeah, so what that means is we can take kind of a half density on here, which is just a constant one, value 1, and we can integrate it over this kind of Lagrangian subspace or relative Calabi-Yau functor. So that's this result. And what we get is exactly this Z mod 2M graded ruling polynomial of the knot, specialized to this particular prime power. And in the previous formula, that was the power of Q, and we don't have that power because we have this sort of twisting built into our formulism. So this proves some conjecture that was in this paper by Ng-Rutherford-Shende-Sivek, who showed the M equals 0 case of that statement, where the left-hand side is just the usual homotopy cardinality. Yeah, maybe I'll not talk too much about the proof, except, yeah, it does involve these two spans and involves tangles. But let me maybe mention some further stuff that maybe for the future. So our formulism is not very conceptual at the moment. Just you write down some formulas and you have some heuristics for how you arrive at these formulas. So it would be nice to have some more conceptual approach or some universal characterization, which tells you that, you know, this formulism is somehow the unique way in which to define things to make some properties work. Yeah, then we would like, there was this original problem. If I have an ADE quiver, how can I get the whole quantum group from the triangulated, the Z mod 2 graded triangulated category? And we don't solve that because it's not odd Calabi-Yau. But maybe there's still something one can do because, for example, this AN category was relative Calabi-Yau already. So there's still more Calabi-Yau structures maybe to be somehow leveraged here. And yeah, another thing one can imagine is going from Legendrian knots to higher dimensions. So if we have an odd dimensional Legendrian submanifold of, like, say, R2M plus 1 or some other contact manifold, then our formulism defines some invariants, which are some kind of higher dimensional analogs of these knot polynomials. And it's not something that we've looked at for what we would get, but yeah, there are some invariants which will depend on this higher dimensional generalization of the augmentation category, which has been defined. Yeah, this I already mentioned, that involving some higher category theory, you would want to generalize everything to n spans or arbitrary n in our formalism. And yeah, I think I'm out of time, so I'm going to end here. Thank you very much.
Yeah, thank you. Okay, yeah, good. Yeah, are there any questions?
I'll let you go first.
Yeah, okay, so to give you more time, so let me ask you just one question. You see this more conceptual approach to formalism. So my question is about formalism for cohomological whole algebra. Some of your constructions, of course, kind of very categorical, yeah. So it looks like it depends that you can choose other realizations if you'd like for motivic shifts on the stack of objects, to say it a little bit. So have you thought about generalizations to
well, yeah, so motivic, I guess it should work. The one thing is if the category, so in your paper on motivic DT invariance, you argue that if your category is proper, then you have this stack of objects. I'm not sure if there's maybe, so if the category is only periodic and you somehow it's less finite, you have infinite x in infinitely many degrees, if that creates some problem for kind of defining the stack of objects. I'm not sure about that.
Well, yeah, it might.
Instead of some polynomial equations, you get just some formal power series maybe. And I think that, so showing that the stack of objects is kind of really algebraic and not just some formal thing.
Yeah, but what about kind of if I use cohomology instead of whatever densities or constructible sheaves?
Yeah, that's already a kind of categorified version, right?
Yeah.
But somehow you don't run into this problem with this infinite product or an infinite sum when you go one categorical level higher up. So I'm not sure in the definition of cohomological Hall algebra, these infinities are really such an issue.
I would rather, I don't know. I'm indeed interested in the definition. You see, this particular question of the double, in your case of whole algebra, but in my case, which I'm interested in, it's cohomological whole algebra. It's still one half of something. And something, this one half is indeed a quantum group, maybe more general, that kind of like shifted Youngians, this kind of things. But it looks like one half of it. And so there should be a universal construction, at least some people believe that there exists a construction of the double. So far, what we are able to do with my collaborators, we can construct, like two representations of our algebra in some huge space, and these two representations they commute non-trivially, so they can be thought of as a representation of the double for which we do not have an independent construction. But it would be nice to have this construction from the very beginning. So a model example for what I'm talking about is this Nakajima construction of the infinite Heisenberg algebra acting on the cohomology of the stack moduli space of all Hilbert schemes of all orders, so it's also infinite for all n of C square. Yeah, so then basically what he does, he constructs two representations of polynomials of infinitely many variables, but they commute non-trivially, so this is how central charge in Heisenberg algebra appears. And so that's we could call it Nakajima double, but I do not have an independent definition. Sometimes we can do it with sort of a quite HOMFLY algebra structure, but this is because probably we know better Drinfeld double. But if there will be a construction like the one which you mentioned with the two periodic complexes, would be really great help.
Yeah, that sounds like a very interesting problem. The only thing maybe I can say is I think there's a similar problem maybe in knot theory, right, where you have the Iwahori-Hecke algebra of tangles, and you categorify that, and then they also want some kind of double of that. I think it's maybe not clear how to define the double of this sort of categorified Iwahori-Hecke algebra.
Yes, and so
that's an interesting thing to think about in the future.
Okay, so more questions?
Yes. So throughout you have been using the finite field, because that can guarantee many of the finiteness requirements. So, for example, the span, you want the F1 and also to be kind of finite, so the fiber finite. So what happens if, and this is also along the question Jens asking, if you replace finite fields to more general algebraic closed field, there will be more interesting, even complex.
Yeah, so I mean, it will be kind of like in the definition of going from the Ringel-Hall algebra to the Motivik-Hall algebra. So there should be some variant of this formalism where instead of counting number of points over a finite field, you sort of count motivically. So
motivically, that will require some of the coefficients will be.
So that everywhere where basically
the Q will have some kind of a polynomial, or at least in the formula you wrote, most of the other series, degree-wise series, the coefficients should be kind of when Q varies, the coefficients will be independent of the Q.
Yeah, so the Q gets replaced by the motive of the affine line, and the main point in all this formalism was kind of the correct power of Q, right? So
that's right.
But I mean, one technical difficulty is that now you need to make sure that really all your spaces of objects have some algebraic structure.
Well, the trouble over there is that the finiteness will completely fill. So the fiber of F1 will have infinity.
But then you just say, like, you declare that instead of counting number of points, you just declare that the fiber is a motive, and that will be the coefficient in your formula.
I thought that because of Ringel's whole algebra, actually yesterday in our junior M seminar, called New Seminar, one of the graduate students was talking on this. So the Ringel whole algebra was using isomorphism classes and then linearize it. So that's what you're using. But there is a dual version of that, which is by Lustig. Instead of taking the linear spans of isomorphism classes, one takes the functions on the, and this is much larger than the Ringel's whole algebra. But this is the advantage that permits you to have infinite sums. So therefore, that's for example your F1 in the two span definition in the formulation, you don't have to require those to be even fiber-wise, even the fibers being finite. As long as you can do some kind of the functions with the compact support, for example.
Okay.
So that so I was wondering what Lustig did was on each fiber instead of well, that's too large, but he has to try to get the smaller parts, which is the one generated by the irreducible ones or the spherical ones. he has to be carefully to construct some kind of category to do that. So I was wondering if you, this approach can be dualized in the spirit of the Lustig's approach called algebra from your setting.
Yeah, that's a good question to which I don't. I'm not familiar with Lustig construction, so I don't know. But I mean, our main thing is the power of Q in the formula. So the guess is that the dual construction is also possible, but yeah, I'm not sure.
Yeah, the dual construction is one part is about the coefficient. The other part is that when you multiply two objects, and the things in the middle, the infinite many will appear. So it's not a finite sum. And also on the part, your question on this constructing the whole quantum group, not just half of it. And the bridge nets give in the quiver case, giving this two periodical complexes. And that's but he still has to mod out some of the relations in constructing the whole algebra, and then have to identify some of the objects, take the quotient of the whole algebra. That's the whole quantum group. I believe like 13 years or 12 years ago, Savage asked the similar question in Manhattan. Earlier, what we did was, instead of using two periodical complexes, we did the different quiver. Having in the quiver case, we have two copies of a quiver, but they are joined by this kind of two double complexes. That was, and you do the whole algebra, and you take the quotient. There is a very nice simple generator to take the quotient, and quotient will be the whole quantum group.
Okay, so the quotient instead of localization as in project.
That's right. Just the localization is also the quotient. And what Reginald did, even though doing localization, was also the quotient.
I see. Okay.
So probably I'll give you more reference afterwards. But definitely, that's a very interesting question. If you, in your setting, you can do this, whether do a quotient or, of course, without quotient, direct construction get the quantum, the entire quantum group. That would be very nice.
Actually, kind of one comment in our definition with Maxim, which is motivic, we do not take delta functions, of course. We consider arbitrary constructible families of objects. So then there is no, it's not necessary to kind of to use this Ringel. It's a different. It's I would say it's a generalization of clever generalization of Toyen's formula, but we deal with constructible, constructible families.
But the algebra is still on as a vector space based on the isomorphism.
No, it's not a vector space. It's a module of the ring of motivic functions.
Yes, it's a. But it's still.
I mean, which can be.
This is still the isomorphism classes of the object.
What?
I mean, the module has a basis over the motivic.
No, I don't know what. I mean, it's huge. It's a very big. This spherical part, like delta functions sitting somewhere, it's a small piece of it.
Yeah.
And so then.
Well, the Ringel whole algebra is for general quiver can be very large, but the spherical part is very, very, very small, even for the.
That's what I mean. That if you work.
Motivic is even larger.
Motivic is larger, but I know only one paper, I believe. Keller was one of his students, actually, I believe Chinese student. They computed the motivic whole algebra, but for a category generated by one spherical object.
I can see computing the motivic ring itself is
Well, it's awful, but they compute it in terms of generators and relations, and it's amazing. It's old paper. I don't remember how many years.
Isn't it just
but,
the tones Hall algebra or the motivic version? Because I know there's one. I think there's one paper, but it's just Toen, the finite field one. Maybe they also have the motivic.
Toens, maybe. You know, I looked at it so many years ago that everything could be mixed up. But I thought that they, if it the one which you remember better, it's one spherical category generated by one spherical object, and it's maybe Toens, but for some reason I thought that it's motivic. But okay, maybe I should look. I should look in Killer's folder and to find. Okay, anyway, more questions? Okay. Yeah, actually there are, I found it, there are two collaborators to N. Yeah, it's K-linear, I don't know. Anyway, okay, if there are no more questions, well, Fabian, thank you very much. So now it's a good advertisement for your paper in the archive because people can study it carefully. Yeah, it's indeed a new way to compute things for odd Calabi-Yaus. Thank you very much.
Thank you, Fabian, for wonderful talk and for carefully preparing all these notes. It's definitely a lot of time spent.
Thank you. Yeah. Thanks for
Okay,
your
so
attention. And,
yeah.